XGBoost is extreme, but so is this webinar. It's totally extreme, yes, StatQuest. Hooray! I'm Josh Starmer, and welcome to the StatQuest webinar on XGBoost in Python from start to finish. This is the Jupyter notebook that we're going to go through today. We're going to use XGBoost to build a collection of boosted trees, one of which is illustrated below, so this guy right here, and use continuous and categorical data from the IBM Base Samples website to predict whether or not a customer will stop using a company's service. In business lingo, this is called customer churn. You can download the telco churn dataset or use the file provided with the Jupyter notebook. And if you want to learn more about the telco churn dataset, you can click on this link in the Jupyter notebook. It's live. Or if you just want to learn more about the base samples, there's all kinds of datasets here that you could use for other experiments in machine learning. So it's a great resource for just testing out these models in general. All right. XGBoost is an exceptionally useful machine learning method when you don't want to sacrifice the ability to correctly classify observations, but you still want a model that's fairly easy to understand and interpret. In this lesson, you will learn about importing data from a file, missing data, including dealing with missing data XGBoost style, which is relatively unique. And then we're going to format data for XGBoost, including using one-hot encoding. And actually, because of the way XGBoost handles missing data, we're going to have a mini StatQuest in the middle of this webinar to explain sort of the specifics of one-hot encoding and how it relates to how missing data is handled. After that, we're going to build a preliminary XGBoost model, and then we're going to optimize parameters with cross-validation and grid search. And then lastly, we're going to draw, validate, and build, obviously, and then we're going to interpret, evaluate the optimized XGBoost model. Note, this tutorial already assumes that you know the basics of Python and are familiar with the theory behind XGBoost, cross-validation, and confusion matrices. If not, check out the StatQuest by clicking on the links for each topic. Also note, I strongly encourage you to play around with the code. Playing with the code is the best way to learn from it. So, the very first thing we do is load in a bunch of Python modules. Python itself just gives us a basic programming language. These modules give us extra functionality to import the data, clean it up, and format it, and then build, evaluate, and draw the XGBoost model. Note, you'll need Python 3 and at least these versions of the following modules: Pandas, NumPy, scikit-learn, and XGBoost. I've got instructions on how to install all this stuff right here, and also instructions on if you want to actually draw that beautiful tree. I've got instructions on how to install GraphViz as well to make it all work out. All right, so this is where we're going to load in the data. Since this is a Jupyter notebook, we can run the Python code by either clicking on the play button, or we can select run selected cells, or we can select this keyboard combination to run the cells. Note, I'm using a Macintosh, so that's my keyboard combination. On your computer, the keyboard combination may be different. So I'm going to run this. And we get a number over here that tells us that we've run the code. So that's great. If by the way, if Python is still cranking away, if you're doing something a little more complicated than loading in some modules, you'll see a star over here while Python is cranking away. But we just get a number, so that's good. Okay, now we're ready to import the data. We're going to load in a data set from the IBM Base Samples. Specifically, we're going to use the telco churn data set, which allows us to predict if someone's going to stop using telco's services or not, using a variety of continuous and categorical data types. Note, When pandas reads in data, it returns a data frame, which is a lot like a spreadsheet. Data are organized in rows and columns, and each row can contain a mixture of text and numbers. The standard variable name for a data frame is the initials df, and that's what we're going to use here. So what we're doing is we're creating a new data frame that we're calling df, and we're setting it to the output of this pandas function, read CSV. So this is a CSV file that we're loading in. So let's do that. Bam. Now that we've loaded in the data into a data frame called df, we're going to look at the first 5 rows using the head function. So this is our data frame df, and there's an associated function called head that we're going to run. And what it does is it prints out the first 5 rows. So it says 5 rows by 33 columns. And when we scroll over, we see all these columns. Not all of them have been printed to the screen. I don't know if you can see there's a ... between gender and contract. And that just means that even though there's 33 columns, we didn't print all of them to the screen. Note, the last 4 columns, churn reason, CLTV, churn score, these are, what are these? These are sort of exit interview data that were collected from people that left telco. And only people that left telco provided answers here. So we don't want to use this data in our prediction because generally speaking, someone's not going to do the exit interview before they leave the company. And so since these things will give us perfect predictive abilities, we want to remove them from the data set. So we do that using the drop function. So we've got data frame. This is our data frame, and we're going to use the drop function. And then we list the columns that we want to drop. We set access equals to 1 to specify that we're dropping columns instead of rows. And we set in place to true, which means we want to modify df, this data frame called df, directly. We're not making a copy of the data frame, and only in the copy is that containing these or without these columns. It has these columns dropped. And then after that, what we're going to do is we're going to print the first 5 rows again, just to verify that we did everything correctly. So let's do that. Okay, so when we scroll over to the right, we see that churn reason and CLTV, those things are gone. Some of the other columns in this data set only contain a single value and will not be useful for classification. For example, this column, count, we just see a bunch of 1s. We can verify that the only value in this column is 1 by, with our data frame, we specify we want to look at the count column, and then we call the unique function to print out all the unique values in that column. And when we run that, we see that the only unique value is 1. So this column, count, only contains 1, and that makes it useless for making predictions. Likewise, if we look at the unique values in country, just looking at it, we see United States a bunch of times. And if we print out the unique values in the country column, we see that the only value is United States. Similarly, in the state column, we see a bunch of entries for California. Let's print out all the unique values in state. Again, we just see one value, California. So that means we can omit count, country, and state from the analysis because they're not going to help with predictions. In contrast, city, a column called city, contains a bunch of different city names. So let's look at that. So yeah, we see Los Angeles, Beverly Hills, Huntington Park, Standish, all kinds of stuff. So we're going to leave city in because city may help us with making predictions. However, we're also going to remove customer ID, and we're going to remove customer ID because there's a different value for every single person. So that's not going to be very helpful for predictions. And also there's a column called lat long, which contains both latitude and longitude of the resident of that was a customer. but we also have separate columns for latitude and longitude. So we don't need the column that merges those two things. So we're gonna drop those columns as well, just like we did before. So we've got our data frame dot drop. So we're using the drop function. Then we pass in an array of the columns that we want to drop. Specify that we're dropping columns instead of rows. And again, just like before, we're using inPlace set to true so that we modify the data frame df itself. And as always, we're going to print out the first 5 rows to make sure we did everything correctly. Hooray! Looks like we did it just right. Okay, now we're down to just 24 columns. Note, although it's okay to have white space in city names, so you see we've got Los Angeles, and there's a blank space between Los and Angeles, and you see that up here when we printed out the unique values for each city name. We've got a blank space between Beverly and Hills and a blank space between Huntington and Park. Those blank spaces are perfectly okay for XGBoost. XGBoost doesn't care, partially because we're going to use one-hot encoding for this. However, we can't have any white space or blank space if we want to draw the actual tree like we did all the way up here. If we want to draw this tree later on at the very end, we need to remove the white spaces. So we're going to do that. Since we know there's a lot of white spaces in the city column, we've got our data frame and we specify that we're interested in the city column. And then we can use the replace function. And this is just a search and replace function like you'd find anywhere else. We're searching for blank spaces and we're going to replace each blank space with an underscore. We set regex to true. Regex is short for regular expression. And if you're not familiar with the term regex or regular expressions, don't worry. Just think of it as advanced features for a search and replace function. And again, just like we've been doing before, we're going to make these modifications in place. So we're going to modify df directly and then print out the first 5 rows to make sure we did it right. There we go. And we see an underscore between Los and Angeles. And we can also print out the first 10 city names, the first 10 unique city names, and verify that we've got underscores between Beverly and Hills, between Huntington and Park, between Marina and Dell and Ray. So we've eliminated those white spaces. Also, we need to eliminate the white spaces in the column names. So we're going to replace those with underscores as well. We do this slightly differently. So we've got our data frame, df, and we specified that we're interested in the columns, not in a specific column, but the column names. And what we do is we convert those column names to strings, and then we call the replace function. And again, this is just a search and replace. We're searching for white space and replacing with underscore. And just like we've done before, we're going to print out the first 5 rows. Bam! So now we see an underscore between zip and code, senior and citizen, tenure and months, etc., etc. Hooray! We've removed all of the data that will not help us to create an effective XGBoost model, and we've reformatted the column names and city names so that we can now draw a tree. Okay, so now we're ready to identify and deal with missing data. Unfortunately, the biggest part of any data analysis project is making sure that the data are correctly formatted and fixing it when it's not. The first part of this process is identifying missing data. Missing data is simply a blank space or a surrogate value like NA that indicates that we failed to collect one or more features, or we failed to collect data for one or more features. For example, if we forgot to ask someone's age or forgot to write it down, then we would have a blank space in this data set next to that person's age. One thing that's relatively unique about XGBoost is that it has a default behavior for missing data. It knows how to handle missing data. It's expecting it. So all we have to do is identify the missing values and make sure they are set to 0. Now, in the webinar that I've given a couple times now, this has confused a lot of people because what happens if there is a 0 already in your data set? I'm going to have a little mini StatQuest about halfway through that shows how we can have zeros that code for things as well as using zero to code for missing data, and it actually works out. And even in situations, I'm just going to show you one scenario, and even if there's some scenario where it does not work out the way I'm demonstrating, I will throw this out as well. The author of XGBoost has said that even when you code something with zero and you use zero to mean missing data, XGBoost still does a great job. It doesn't, so for some reason, that doesn't really interfere with how well it performs. So the first thing we're going to do is we're going to see what sort of data is in each column. This is what I always do when I'm looking for missing data. I print out the data types for each column because that can tell us if something is messed up or not. We see that a lot of the columns are object, and that's okay because above here, when we did head, we saw that senior citizen has a bunch of no's and it probably has some yeses in there. Partner has yeses and no's. Dependents has yeses and no's. And so it makes sense that a lot of these columns are object because they have text responses like yes and no. However, we should always verify that we're getting what we expect in each column. So for example, we'll look at the phone service column and we'll use our handy unique function to check to see what we're getting. And what we get is yes and no. And that's perfect because that means there's not question marks in this column. There's not an NA placeholder for a missing data. So we can verify that this column only contains yeses and nos, and that's great. Okay, now in practice, we should do that for every single column. Verify that it has the type of data that we're expecting and it only has the responses that we're expecting. And trust me, I did this, but right now we will focus on one specific column that looks like it could be a problem, and that's total charges. So if we looked at this output over here, we see that total charges looks like a bunch of numbers. However, if we look at the data type for total charges, we see that it's an object. And that we usually get that object when we get a mixture of numbers and characters. So one thing we can do is just print out the unique values and total charges and kind of see what we see. So let's do that. Bam. And when we do that, we see that there are too many values to print. We've got this dot, dot, dot right in the middle. But what we see looks like a bunch of numbers. However, if we try to convert the column to numeric data or numeric values, and I'll try that right here, when we run this code, we get an error. So I'm going to comment it out just in case you want to run all the code all at once. And let's look at this error. The nice thing about this error, and the reason why I wanted to show you this error, is it actually tells you what's wrong with the data. It says unable to parse string, quote, nothing, or blank space, end quote. And what does that tell us? That tells us that there are blank spaces in this column in total charges. And so we need to deal with those. Okay, so now we're ready to deal with missing data, XGBoost style. Like I've said before, one thing that's relatively unique about XGBoost is that it determines default behavior for missing data. So all we have to do is identify missing values and make sure they are set to 0. However, before we do that, let's see how many rows are missing data. And if it's a lot, then we might have a problem on our hands that is bigger than what XGBoost can do on its own. And if it's not that many, we'll just set them to 0. So we do this by searching for, we're using the location function. So we got our data frame and we say, give me the rows where this is true. So the value in the total charges column is equal to 0. And then we're wrapping all of that in the len or length function, and that counts the number of rows that have blank spaces in the total charges column. And we see there's only 11 rows that have missing values. So since it's only 11, we can look at them. So we're going to print them out. Bam. So we see, if we go over here, we see that in the total charges column, we have no values. We also see that in the tenure months column, we've got 0 for everybody. And that means that the reason why these people have total charges equal to blank is that they have not been charged for anything yet. They just subscribed. And so they're on a plan. We've got an expected amount of money we're going to be getting from them, but they have not paid us anything yet. And since it's just a handful of people, we're going to set these total charges we're just going to set total charges to 0. And the way we do that is a lot like what we did before, only this time we're specifying, instead of having loc return the entire row, which is what it was doing before, we're specifying that we just want the total charges. And again, we're interested in just the locations where total charges equals blank space. And we're setting that value in the total charges column to 0. So let's do that. We can verify that we modified total charges correctly by looking at everyone who had tenure months set to 0. Note, I'm not looking at total charges equal to 0 because there could be other people that have not paid a dime. Even though they've been on board for a couple of months, they might have zeros there already. But I'm pretty certain that everyone who had tenure months equal to 0 had a blank space because they just signed up and they hadn't paid a bill yet. So we do that and we see that we've got the tenure months equal 0, and when we scroll over to the right, we've got total charges equal to 0. So that worked. Bam! We have verified that our data frame DF contains zeros instead of spaces for missing values. Note, total charges still has the object data type, and that's no good because XGBoost only allows int, float, and Boolean data types. So we're going to fix this by converting that column with toNumeric. There are multiple ways to convert columns from one type to another. This is just one of them. So I'm using toNumeric, and it's a pandas function. And I'm specifying that I want to convert the total charges column, and I'm saving it in the original total charges slot. And when I'm done, I'm printing out the data types to verify that we've done it correctly. So let's do that. Bam. And we go down here and we see total charges is now float 64. So hooray! Now that we've dealt with the missing data, what we're going to do is we're just going to replace all of the other white spaces in all of the columns with underscores. There could be other columns that have white spaces, and we're just going to do this all at once. So we're going to do it just like we did before. We've got our data frame and we're using the replace function. However, this time we're not specifying a specific column. We're just going to do this data frame wide. We're replacing blank space with underscore, and then we're going to print out the first 5 rows to verify that we did it correctly. So there we go. Bam. And if we scroll over to the right, we see that one of the things that we fixed was under the payment method column. Instead of blank spaces between mailed and check, now we have an underscore. In electronic and check, we've got underscores. So bam. And remember, just to clarify, the only reason why we're replacing all these blank spaces is so that we can print out a nice, pretty looking tree. XGBoost itself doesn't really care, partially because we're going to one-hot encode these things later anyways. Okay. So now that we've dealt with all those issues, we can now start formatting the data for an XGBoost model. And the first step is to break it into 2 parts. We want to separate the columns that we will use to make classifications from the column that we want to predict. So we're going to use the conventional notation of capital X to represent the columns of data that we will use to make classifications. And we're going to use lowercase y to represent the thing that we want to predict. In this case, we want to predict churn value. Let's look at this. This is 1 for people that left, and it's 0 for people that did not leave. And And so what we're doing is we're creating uppercase X here, and we've got our data frame, and we're just like before, we're calling the drop function, and we're specifying that we want to drop churn value. However, we're not doing in place like we did before, and we're saving the results in a new variable, and we're going to print out the first 5 rows of that new variable. So there we go. And if we scroll over, we see that churn value is missing. We've got everything else, which is great. That's exactly what we wanted. Now we're going to make this lowercase y variable, and it's going to be just the column in data frame called churn underscore value. And then we're going to print out the first 5 rows to verify that it looks the way it should. And there it is. Bam. Now that we've created capital X, which has the data that we want to use to make predictions, and we've made lowercase y, which has the data that we want to predict, we're ready to continue formatting X, or capital X, so that it is suitable for making a model with XGBoost. So that brings us to one hot encoding. Okay, now that we've split the data frame up into 2 pieces, we need to take a closer look at the variables within capital X. So the list below, which I got from the IBM website for this data set, tells us whether or not each column should be a float or categorical. So we see city is a category, longitude is float, gender is a category, senior citizen is a category. We've got a bunch of categories. Tenure months is a float. So we've got lots of columns. Now, just to review, we're going to look at the data types in X to remember how Python is seeing the data right now. So we see that latitude, longitude, monthly charges, and total charges, those are all float 64, which is great. That's exactly what we want. However, all of the other columns that are object, those need to, we need to inspect those to make sure each one only contains a reasonable value. And then we also need to modify them with one-hot encoding. One-hot encoding is a trick for taking data that is categorical and splitting it up into a format that XGBoost and a lot of other algorithms can use. So the problem is that XGBoost and a lot of other machine learning algorithms, they natively support continuous data like monthly charges and total charges, but they do not natively support categorical data like phone services, which has 2 different categories. So if we want to use categorical data with our model, we have to convert it with one-hot encoding to kind of get around this limitation. Okay, so at this point, you may be wondering, what's wrong with treating categorical data like continuous data? Can't we just convert the categories to numbers and be done with it? And to answer this question, we're going to look at an example, and I've chosen payment method to be that example. We see it has a bunch of options. We've got mailed check, we've got electronic check, we've got bank transfer, and we've got credit card. If we converted those categories to numbers 1, 2, 3, and 4 and treated them like continuous data, then we would assume that 4, which means credit card, is more similar to 3, which means a bank transfer, than it is to 1 or 2, which are other forms of payment. That means the XGBoost tree would be more likely to cluster the people with 4s and 3s together than 4s with 1s. In contrast, if we treat these payment methods like categorical data, then we will treat each one as a separate category, and that is no more or less similar to any other category. Thus, the likelihood of clustering people who pay by mailed check with people who pay by electronic check is the same as clustering with mailed check and credit card. So this approach seems more reasonable to me. Note, there are many different ways to do one-hot encoding in Python. There are 2 main popular ways, and I describe the pros and cons of these 2 approaches in the Jupyter Notebook in this paragraph. However, for the purpose of this webinar, we're going to use get dummies because I feel like it's the best way to teach what one-hot encoding does. So what we're going to do is we're going to use this pandas function. So PD is short for pandas. We're going to use this pandas function called get dummies. And we pass in the data frame that we're interested in processing, and the columns that we want to one-hot encode. Now, I'm not saving the results. I just want to see what happens. So I'm just going to print out the first 5 rows to show you how this column payment method is one-hot encoded. So we run this code and we see that all the columns that we did not modify are on the left side of the data frame. But if we scroll to the right, we see payment method, bank transfer. So we've got that column. We've got another column for payment method credit card, another column for payment method electronic check, and another column for payment method mailed check. And in each column, we've got a 1 if for in the bank transfer column, we've got a 1 if they use bank transfer and a 0 for any other option. For credit card, we've got a 1 in that column and a 0 for any other option. For electronic check, we've got a 1 in that column and 0 for any other option. And lastly, for mailed check, we've got a 1 in that column and 0 for any others. Note, if you're familiar with linear regression or logistic regression, if you're not familiar with linear regression or logistic regression, don't worry about what I'm about to say. But if you are familiar with those two things, one-hot encoding is different from the way you would encode it for the same data. The one-hot encoding gives us a result that is different from what we would do for linear and logistic regression. So just keep in mind that one-hot encoding is not for linear and logistic regression, but it works great for trees. So now that we know what getDummies does and we know that it works, we're going to use it on all of the categorical columns and we're going to save the result. And note, in a real situation and not in a tutorial like this, we would go through each individual column and make sure it only contains reasonable data. However, since this is just a tutorial and I've already done all that work, we're just going to skip to the next step, which is to run this pandas function, PD. We're going to run the pandas function called getDummies. We're going to pass in our data frame and all of the columns that we want to convert into categorical, all of the categorical columns. And we're going to save that in a new data frame called x_encoded. And then when we're done, we're going to print out the first 5 rows. So let's do that. Bam. So now we see that we've encoded a bunch of columns. There's this ... still because there's too many columns to print. And if you look down here, obviously we've got 5 rows because we use the head function, which only prints out 5 rows. But we now have 1,178 columns. Dang. A lot of those are because we've got a different column for each city name. So you see all these city names that just kind of bleed into the ... We've got a lot of different city names and we've got a column for each one. Now, one last thing before we build an XGBoost model. We're going to verify that Y only contains 1s and 0s with a unique function. So we've got y.unique and we run that and it only has 1 and 0 and that's a double bam. So we've finally finished formatting the data for making an XGBoost model. However, before we do that, I want to do a mini StatQuest to show how one-hot encoding works, especially when we're coding missing values with 0. So, imagine the favorite color was a column or feature or variable in our data set. 2 people loved the color blue, 2 people loved the color green, and 2 people had missing data. So, just like we did in the Jupyter Notebook, we replace the missing data with 0s. Now we convert favorite color with one-hot encoding, just like we just did. There are 1s in the blue column for the 2 people that liked blue, and 0s in the green column because those people did not like green. Likewise, there are 1s in the green column for the 2 people that liked green, and 0s in the blue column because those people did not like blue. Lastly, both the blue and green columns get 0s for the people with missing data. Let's move this table to the left side. Now the question is, should the people with missing data be clustered with the people that like blue? Or should they be clustered with the people that like green? XGBoost answers these questions by comparing these two different ways to split the data. On the left side, we are splitting people who like blue from everyone else. And that means we are clustering the people who like green with the people with missing data. On the right side, we are splitting the people who like green from everyone else. And that means we are clustering the people who like blue with the people who have missing data. XGBoost then chooses the split that gives the best value for gain. Okay, I get how XGBoost deals with missing data. But doesn't keeping track of all these zeros take up a lot of memory? Because XGBoost uses sparse matrices, it only keeps track of the ones, and it doesn't allocate memory for the zeros. And that means that this branch is really just checking to see if memory is allocated for blue. If memory is allocated for blue, then we go to the left. And if memory is not allocated for blue, then we go to the right. Likewise, this branch is only asking if memory is allocated for green. If memory is allocated for green, then we go to the left. And if memory is not allocated for green, then we go to the right. This is how XGBoost deals with missing data and is memory efficient at the same time. Bam! Alright, now let's return to the Jupyter Notebook and build our preliminary XGBoost model. Okay, so I know we just said that we were going to build the XGBoost model, but the first thing we need to do is we need to split the data into training and testing data sets. However, let's first observe that this data is imbalanced by dividing the number of people who left the company, where y equals 1, by the total number of people in the data set. So since this column y, lowercase y, only contains zeros and ones, and it only contains ones for people that left the company, we can add up all the values in this column to get the number of people that left. And if we divide it by the length of that column, we'll get the percentage of people that left. And we see that only 27% of the people in the data set left the company. Because of this, when we split the data into training and testing data sets, we will split using stratification in order to maintain the same percentage of people who left the company in both the training set and the testing data set. So we're using a function called train_test_split, and we're passing in x encoded, lowercase y. We're setting the random state to 42 so that hopefully, hope against hope, you will get the same results that I got. And we're setting stratify to y for yes. And this will return 4 variables, and or four data sets. We're storing them in x_train, x_test, y_train, and y_test. So let's run this. Bam. Now let's verify that stratify worked as expected. Now we're just doing the same math we did before, only this time we're doing it on the training data set. So we see that 27% of the training data set contains people that left. And let's look at the testing data set. And we see that 27% of the people in the testing data set left. So bam, stratify worked as expected. So now what we're going to do is we're ready. We've got our training set. We've got our testing data set. We're ready to build our XGBoost model. And the way we do that is we use XGB, which is the XGBoost module or library. And we use a function called XGB classifier. And we specify that the objective is binary logistic, and that's for classification. Because XGBoost kind of uses a logistic regression approach to evaluating how good it is at classifying the observation. We're setting missing to none. The default value for missing is none, so I don't actually need to set this. And in the webinars, this confused a few people. The purpose of this parameter or this argument is to tell XGBoost what character we're using to represent missing values. The default value when you have missing equals none, the default value is 0 or NP, or it's a numpy, not a number, but it uses zeros in that sparse matrix, just like we saw in the mini StatQuest. It uses zeros to represent missing data, so it doesn't have to allocate memory in those fields for people that have missing data. So that's the default behavior, and that's what we're specifying. If we used question marks to represent missing data, we could specify that here. And again, we're setting the seed to 42 in order to hopefully give you the same results as me. We store this in a new variable. So this is just basically creates a shell within which we're going to create a forest of extreme gradient boosted trees. And we're storing that in this variable. And we create those trees by then running fit. We pass in the training data. We say be verbose, sort of tell me what you're doing while you're doing it. And one thing we're doing that's kind of special is we're doing early stopping. So what we're doing is we're building trees, and at some point the prediction will not improve. And then what XGBoost is going to do is then it's going to build 10 more trees. And if those 10 all 10 of those trees, none of them can improve on the predictions, then it will stop. And we're using the AUC as a way to evaluate how well the predictions are being made, and we pass in the testing data set because it's training the trees on the testing data set on the train. Excuse me. It's training on the training data set, but it's evaluating how many trees to build using the testing data set. And this is what we would normally do anyways by hand using cross-validation and a variety of other approaches, but XGBoost will do it for us. Okay, so you'll see there's a star by the code, meaning it's running, and you can see down here we're just sort of printing out the results of each tree, and we're going and going and going. And here we finally stop after building 55 trees. However, that meant that the previous 10 trees did not improve the classification. And so it says stopping. The best iteration was actually after building 45 trees. So we've only created 45 trees for our model. Okay, so we've built an XGBoost model for classification. Now let's see how well it performs on the testing dataset by running the testing dataset down the model and drawing a confusion matrix. We do this with the function called plot confusion matrix. We pass in the model, the extreme gradient boosted trees, and we passed in the testing data sets. And then the last two rows of stuff just make the confusion matrix, excuse me. It just makes the confusion matrix look pretty. So in the confusion matrix, we see that the top row represents people that did not leave the company, and there are 1,294 people in this row. And of those, 1,178 were correctly classified. So that's awesome. That's 91%. However, the second row, these are the people that left the company. And there are 467 people in this row. And we see in this bottom right-hand corner that only 239 or 51% were correctly classified. So XGBoost was not awesome. Part of the problem is that the data is imbalanced. And we saw that earlier, and we see that in the confusion matrix right now. Because people leaving the company costs the company a lot of money, what I'm going to do is I'm going to try to optimize the XGBoost model so it does a better job predicting people that have left or are leaving the company for a competitor for some other reason. And the good news is XGBoost has a parameter called scale, pause, wait that helps deal with imbalanced data. And basically what it does is it adds a penalty for incorrectly classifying the minority class. In this case, that's the people that that left the company, and we want to increase that penalty so that the trees will try harder to correctly classify them. And so we're going to try to improve our predictions using cross-validations to optimize these parameters. Okay, so XGBoost has a lot of hyperparameters. These are parameters that we have to manually configure and are not determined by XGBoost itself. And these include max depth. Max depth is how deep the tree can go. So if it's just a stump, then we just go down one level. If we allow more branching, then we can go down 2, 3, 4, 5, or 6 more levels. We can optimize the learning rate, which is eta. And if you've watched the StatQuest videos on XGBoost, you know all about that. We can also optimize gamma, the parameter that encourages pruning, and the regularization parameter for lambda. And that's for ridge regression. So let's try to find the optimal values for these hyperparameters in hopes that we can improve the accuracy with the testing data set. Since we have a lot of parameters, we're going to do that using GridSearchCV or cross-validation. However, because this is just a tutorial, I've commented all this out. This takes a while to do. It takes about 10 minutes to run. However, there's a few notes in here that I want you to be aware of. In the manual for XGBoost for XGBoost, it says if you have imbalanced data, then you should use the AUC to evaluate the performance of your of the fit, and that we should also try to optimize this scale pause weight parameter. And what I've done is I've commented all this out, but I've done the optimization in 2 separate rounds because optimizing everything all at once just took too long. So what I did is for max depth, I gave it 3 different values, 3, 4, and 5. So we can have a tree that's got 3 levels or 4 levels or 5 levels. I've got 3 different values for max learning rate that we can try out, 3 different values for gamma, 3 different values for the regularization parameter, and 3 different values for scale pause weight. And then I optimized. Here's something I need to point out. In order to speed up the cross-validation, for each tree, we're using a random subset of the actual data. We're not using all the data. We're just using 90%, and that's randomly selected per tree. We're also only selecting per tree 50% of the columns in that data set. So for every tree we make, we select a different 50% of the columns to make that tree. And that helps with overfitting, and that also helps speed things up considerably. Other than that, we're just doing, we're using the AUC to score, and we're not doing a lot of cross-validation. We're not doing 10-fold, we're just doing 3-fold, but you get the idea of how we're doing it. So when I ran this, when I ran the first round, it gave me a max depth of 4, which is the middle value here. We could have gone down as low as 3, and we could have gone as high as 5. Because I got the middle value, I set that value in the second round. However, for learning rate, I got a value on the edge of the range. So these are values that so this is on the sort of the high end for the learning rate, but it could go higher. And so what I did is, because it's possible that it could go higher, I continued to explore in that direction the next time I went through a cross-validation. Likewise for gamma, the first time we got the middle value, so I just set gamma to 0.25. But for the regularization parameter, we got 10, and so I continue to explore with larger values for the lambda. But it did settle on scale pause weight for 3, and so we're just going to stick with that. And so when so then I just ran the second round, and ultimately I got gamma equals 0.25, the learning rate equals 0.1, max depth equals 4, and regularization parameter is 10. Okay, so now that we've optimized the parameters, we can build the final XGBoost model. And now this call to XGBoost classifier is a little more complicated because we're specifying a lot more of the parameters here. Because we're not just using default settings now, we're using the ones that we optimized. We're using early stopping just like we did before, and that means we don't have to optimize the number of trees that we're going to use in the random forest. So we'll run this, and it's going. Doop boop boop, doop boop boop, doop boop boop, doop boop boop, beep boop boop boop, beep boop boop boop, beep boop 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 boop, beep boop boop, beep boop 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 boop. And there it is. It stopped after making 65 trees, but remember, that means there were 10 trees that did not improve before that. And so it says that the best iteration was the 55th. So it built 55 trees, and that's where it's going to end. Now let's plot the confusion matrix. This is just like before. And now we see that we're doing a much better job classifying people that left the company. Now we've captured 390, that's 84%. Before we were only getting 51%. However, this improvement comes at the expense of correctly classifying the people that did not leave. However, the company may feel differently, and that's fine with them. But from my perspective, since this is my tutorial, the way I see it is when people leave the company, they take their money with them, and that's money that the company does not get. And so it'd be nice to be able to catch those people before they leave and then send them a coupon for a milkshake or an ice cream cone. And maybe if we do that, they'll stick around and they'll continue to pay us every month for their internet and their telecommunications needs. Now, like I said, we're not doing such a hot job predicting people that aren't going to leave, but that's an error I'm willing to make. And so what this means is maybe I'll send a free coupon to someone who isn't going to leave the company. They'll get a free ice cream cone or a free milkshake or something like that. And that's just going to make them feel better about the company. They're going to be, hey, I really like this telco company. They give me milkshakes every now and then. So I feel like we're making errors, of course, but we're making better errors than we were making before. Okay, the last thing we do is draw the tree. This code right here where we're creating the XGBoost container and then training, everything is the same as before except for this thing, which is key, which tells XGBoost that we only want to build one tree. We don't want to build 65 trees or 55 trees. We just want to build one because all we want to do is draw that first tree. Now, why do we want to draw this first tree? One reason we might want to draw it is, say like we don't have an idea of what are some reasonable values to set for the cross-validation for those parameters for the regularization or for all these things or for gamma. Printing out the first tree can give us a sense of what a good ballpark is. We'll see what the values are. We'll see what the gain is. We'll see what the weight is. We'll see what the cover is. We'll see all these things. And those will give us a starting point for optimizing these parameters when we go back to optimize the tree. But we've already optimized the tree, but it's still kind of cool also to look at the tree as well. So we're going to, down here, I've just got stuff that makes the tree pretty. I've also got stuff for printing out sort of numerically how that tree performed. So here's what we're going to do. We're going to run the code, and these are our metrics for how the tree did, and these are some of the values that we can use to help us figure out what values we need to use when we're optimizing the tree. And here's the tree itself. And I know it's really hard to see the individual values inside of these boxes, so I'll just tell you what they are. In the root, so in each of these green nodes, we have a column name and we have a threshold for splitting observations. In the root node, we have contract, month to month, less than 1. And that means all of the people where that's true, where the value in that column was less than 1, they go to the left. And all the people where that statement is false, they go to the right. And actually, when we draw this tree out, it's hard to see, but there's a little no there, and on the branch that goes to the right, and on the branch that goes to the left, there's a little yes, comma, missing. So that means people that have values less than 1 for month to month, plus the missing data, as we saw before, are going to go to the left. So that's how to interpret the tree. The leaves, they don't give us classifications. Remember, this is XGBoost, and the leaves just give us sort of a small incremental piece of probability that we add together for all of the trees. And that gives us the final probability that an observation is one classification or the other. They're either going to leave the company or not. In conclusion, we have loaded data from a file, identified and dealt with missing data, formatted the data for XGBoost using one-hot encoding, built an XGBoost model for classification, optimized the XGBoost parameters with cross-validation and grid search, built, drew, interpreted, and evaluated the optimized XGBoost model, and that gets us to the triple BAM. Hooray! We've made it to the end of the Jupyter Notebook. I want to thank all of you guys for supporting StatQuest, and it just means a lot to me that you'd be willing to show up for a webinar, and I hope you're all safe, and until next time, quest on!